Hello, this is Mrs. Hedden again with Chapter 14, Notes number 7, the last video for the chapter. And I've got 3 worked heat transfer problems. The first one, the world's most active volcanoes, such as the one in Hawaii, can disgorge about 5 times 10 to the 5th cubic meters of 1,300 degree centigrade lava per day. What is the rate of heat transfer out of the earth by convection if this lava has a density of 2,600 kilograms per cubic meter and eventually cools to 30 degrees C? Assume that the specific heat of lava is the same as that for granite. So we've got the volume is equal to 5 times 10 to the 5th meters cubed per 1 day. We have the initial temperature. We're hunting for the heat transfer rate, Q over T. We know the second temperature is 3 degrees C. We have the density, and we have 3 equations. Of those 3 equations, there's nothing about radiation. So this guy is really for radiation. That doesn't look too good. There's really nothing about convection, but there is convection. But we don't have an area. We do have a delta T. We don't have a D. It doesn't look real good. So that kind of leaves us with this guy. So we're going to look at this Q, figure out the Q, and then we've got a time for the volume. The time is per day. And we can, as long as we've got a time, we can put Q over T and find Q over T. So we're going to try this route first as being the more likely one, because trying to figure out an area from this volume is going to be really tough. All right, from table 14.1, and it tells us to use the specific heat of lava as the same as gravity. And by the way, that's the other clue that that formula might be the same, is they're talking about specific heat here. So I look that up, and I go ahead and say, but in order to use this guy, I have to first find the mass. But we know how to find mass. We have a density, so we can find the volume. We've given that. We've got the density. We're given that. And so mass is equal to density times the volume. And so the mass is 1.3 times 10 to the 9th kilograms every day. But we're going to have to get a rate, and the rate's usually done in seconds. So you might as well change that per day to seconds right away. And then we have the mass over time, which is 1.5 times 10 to the 4th kilograms every second, which is still a heck of a lot of mass per second. So now we've got a mass over time. Now we can go back and start looking at this guy. And so I've got the C from table 14.1. I've got the mass. I've got the C. I've got the change in temperature. And I've got 1.6 times 10 to the 10th joules is lost by the lava every second, or Q over T. That gives us 1.61 times 10 to the 4th megawatts. And we can only put it in megawatts if we had done this to seconds. And that gives us the answer. Yay. On to the next one. Suppose you stand with 1 foot on ceramic flooring and 1 on a wool top carpet, making contact over 83.0 cubic centimeters area with each foot. Both the ceramic and the carpet are 2 centimeters thick and are 10 degrees centigrade on their bottoms. At what rate must each foot supply heat to keep the top of the ceramic and carpet at 33 degrees C? And it asks for the wool carpet. But first I'm going to go ahead and write down what I know. So I've got all this stuff. I changed it to cubic meters for the area. I changed the distance to meters. I've got the first temperature, and I've got the second temperature. And again, I've got the same 3 formulas. This is a rate. This is a rate. And we can see how we cleverly can make this one into a rate. Which one are we going to use? Well, now we've got a distance and we've got an area. So it certainly looks like this guy is going to be the route to go. So the first thing I'm going to look at is ceramics. And of course, I go to ceramics, I look on the table, and I cannot find anything for K for ceramic. So I took a wild guess that it would be the same or very similar to glass and concrete, because glass and concrete have the same K. So I made a wild leap. also tried looking on the internet and they just gave me a range, but I tried this one first then. So Q over T is equal to my hopeful K times my area, which converted to cubic meters, times my difference in temperature, divided by my distance, converted to meters. Okay, and by the way, I have to have these in meters because this K has a meters in it. All right, and that gives me 8.02 joules per second, or 8.02 watts, because a joule per second is the same as a watt. And I checked, and that's correct. So my guesswork of using glass or concrete for ceramic worked. All right, wool was on table 14.3. So K for wool is 0.04, which is substantially less than glass or concrete, which gives us a substantially smaller transfer rate of only 0.382 watts, which is why when you stand on a wool rug, your feet don't get cold as fast as when you stand on ceramic, tile, or glass floors. On to the third one. Okay, suppose you walk into a sauna that has an ambient temperature of 48.0 degrees centigrade. Calculate the rate of heat transfer to you by radiation given your skin temperature is 37 degrees, the emissivity, which I still can't pronounce, of the human body is 0.98, and the surface area of your body is 1.35 meters squared. Okay, this one is giving you a hint. It says by radiation. So again, given those three equations, we're probably going to use the one with radiation. Also, we're given this guy, little e. So I've got the area of my body. I've got the temperature of the surroundings, which is T2. I'm hunting for the rate. The temperature of the object is T1. And notice I finally have to convert these guys to Kelvin. Little e is 0.98. There's my equation with that wonderful T to the fourth. There's this guy, which is not going to work, and this guy, which is not going to work. So we go ahead and plug everything in. And by the way, when I gave you the units for the constant here, I didn't put these guys in the denominator, and they belong in the denominator. Okay, so I've got sigma, or the constant. I've got E for the body. I've got the area of the body. And I've got the temperature of the surroundings to the fourth power in Kelvin minus the temperature of the object to the fourth power in Kelvin. I multiply all those things together and I get 103.69 joules per second, or 103.69 watts, basically. So that's the answer to part A. Going on to part B, if all the other forms of heat transfer are balanced, they're net zero, at what rate will your body temperature increase if your mass is 68 kilograms? So you walk into your sauna, how quick, at maybe a 97.8 degrees, how quickly is your body temperature going to go up? Let's take a look. We got again these guys, right? We're really hunting for the change in temperature over time. So we're hunting for how fast my body temperature increases, and a rate is per time. So delta T over T. We've got these guys. We've got this guy from part A. Q over T is 103.69 watts. And using this formula here, okay, I divide both sides by T. So I've got a little t on this side, T being time, little t. All right? So then I've got delta T over T. I've got Q over T, which I know. So that's this right here. This is my unknown. And then I divide, I get delta T over T by itself, dividing both sides by 1 over MC. So that is where this thing comes from. Once I figured this guy out, then it's just a matter of plugging and chugging. I plug in Q over T, got from the previous problem. I'm using joules per second instead of watts, so all the units look nice. 1 over MC, got that. And I get 0.000436 degrees centigrade per second, which is not too handy, which is why they're asking for it per minute. And it's 0.026 degrees centigrade per minute that your body temperature goes up. If you want to change that to Fahrenheit and figure out how fast your body temperature goes up and how long you should stay in a sauna, go for it. And that is the end of the last video notes for this chapter and the end of the 3 worked problems. Thank you very much for your time.